non-commutative integrable systems.
Thank you. I would like to thank organizers for allowing me to speak and present my results. I will tell you something about non-commutative integrable systems. Non-commutative for me is that I use variables which totally do not commute. What are my reasons? First reason is that I am somehow guided by some geometric principles, some geometric considerations, and some of the geometry incidence theorems can hold on in geometries, projective geometries over division rings. So what is division ring? Just a field, but the multiplication doesn't have to be commutative. And so geometry was my first motivation. Second motivation is that I'm trying to understand or connect classical integrability to quantum integrability. And it turns out that many quantum algebras, like the standard ones, admit division rings of fractions. Yes. Okay. So the basic system I consider is the Hirota equation, but for non-commutative variables. And what is geometric meaning? I start from n-dimensional, it is n hat here, n-dimensional integer lattice, and I consider maps to n-dimensional projective space such that 3 points, so point phi of n, its neighbor in ith direction, so here is the convention of shifts, and its neighbor in j direction, so it's here, are collinear. Just that simple principle. 3 points are collinear. We are in a projective space, so we know what the straight line is. Maybe some of you know that many years I developed a theory in which the basic principle was that 4 points are coplanar. Now I switched to 3 points are collinear. So even something more simple. Okay, so if you add a third variable, nk, yes, so you put its neighbor here, phi k, and you can put phi translated in I and j variable somewhere here, yes, and then ik neighbor of phi I must be on the line, yes, and now you find that this seventh point of this configuration is uniquely determined by intersection of these two lines. Yes? So this is how the nonlinear equations appear, and similar picture appeared earlier in a bit different context, but very much related with works of Konopelchenko and Schiff. Okay, but now we would like to have equations. So what we do? We go to homogeneous coordinates. We know that in projective geometry we use homogeneous coordinates. So we can, what we do, we consider point of a projective geometry as a class of equivalence of vector in a vector space of 1 dimension more. Yes, so you can rescale that vector arbitrarily as you want. So we consider homogeneous representatives of the map. So here is m plus 1 dimensional vector space over a division ring. D is a division ring, so non-commutative field. Yes. And we fix that we multiply the vectors from right. In the non-commutative projective geometry, it is important to have left or right. It doesn't matter, but you have to choose. Yes, and now the collinearity of these 3 points is translated into a linear equation which involves these 3 vectors. Yes, and Aij are some coefficients. Yes, and what you do usually to have that restriction, you add third variable, you make compatibility condition, and you obtain a system of equations for these fields Aij. So the fields Aij are fields in a division ring. Okay. But usually you know that you can rescale your homogeneous coordinates, and then you obtain the corresponding transformation of the fields Aij. Yes? And it turns out that there is a very nice gauge fixing. So usually in projective geometry, if you would like to make some calculations, you have to fix your gauge. So somehow it is convenient and it is possible to find such a rescaling here that these Aij fields are related in such a simple way. Yes, it allows to introduce somehow new field. Yes, and we obtain the linear equation in this form. So from this to this, and this the form I will use. But I would like to mention that if you would like to make quantum things, then sometimes it is better to keep the full gauge freedom. Because if you make some commutativity assumption for some variables, making gauge or fixing gauge, you destroy some nice gauge, some nice commutativity relations. Okay, so this is a linear system for the non-commutative Hirota-Miwa equation. I think it was first time written by John Nimmo. Okay, and this is the nonlinear equations. Yes, and here you take in the linear problem a pair of I and j. Yes. Any two pair you have a linear problem. This is a compatibility. So this is trivial. This is somehow also trivial because from ij and ik you can obtain jk linear problem. And from this equation you infer that there exists a potential rho. Yes. And I would like to remark something which at the moment is trivial but will have consequences. That we can still gauge the function phi, capital Phi, preserving the structure of the linear problem. But now the gauge function should obey such a simple equation, which means that it should be a function of a sum of all variables. Yes? Okay. And now to have connection with something which everybody knows. So when the field is commutative, you can introduce another potential such that all these functions uij are expressed in terms of one single potential. Is the tau function, and what remains? It remains this equation, which gives the famous Hirota equation. Yes. And it turns out that one can introduce the non-autonomous version of the system by some clever trick which gives a system. So here the functions ai are arbitrary function of ni, yes, of a single parameter. And for full without any reduction, both systems are equivalent. Okay. But now we go back to the non-commutative business, and we somehow distinguish one variable, yes, because we have the linear problem in all pairs of variables, but now I would like to have the linear problem in that distinguished variable and other variable, yes. So the last and I, yes, and we have the last and j, then we have the linear problem with I and j. So we do not lose anything, yes. And also I distinguish one potential, so one index of the potential, yes, related to that last variable, which now I write explicitly, yes. Okay. So the last variable and any other I. Okay, and now the linear system transfers in to such a form, and this is no, on the commutative level. I found it in the work of Kajiwara, Naomi, and Yamada. Yes, and one gets nonlinear system for these coefficients, which is equivalent to the previous one, in fact. And again, like before, this allows to define you a potential, Rk, and what remains is a system for these potentials. Yes, and what is the structure? So k is explicitly written last variable. So k is a variable from z, yes, and ni and nj are hidden in that n remaining part. Okay. So this system is equivalent to that Hirota equation in the work of Kajiwara, Naomi, and Yamada. It can be said that it is the non-commutative KP hierarchy, following the nomenclature. Okay, and I would like to mention that what about higher dimensional compatibility or consistency of the system? Not entering into details, somehow if you would like to have now four variables, yes, so that distinguished and IJL variables say that if we would make the geometrically compatibility conditions, we will find that something can be constructed in three different ways.
Does the distinguished variable play the role of x in the continuous case?
Not. But it may, but in my approach it doesn't. Okay, and it turns out that this point phi k ijl can be constructed in three different ways, and all these different ways coincide, and this is the statement which is just the so-called Desargues theorem of projective geometry, and somehow it was first observed by Wolfgang. I was somehow indirectly via a talk of Sasha Bobienko, I was informed about that the Schwarzschild KP compatibility multidimensional compatibility has combinatorics of the Desargues theorem. Yes, so it was one of my starting point, because for I think 2 or 3 years I was looking for some system related to Desargues theorem, and I jumped on that. Okay. But now, what we can make periodic reduction in that distinguished variable. Yes, okay. And periodic on the geometric level. Yes. But what we know that on the calculation level of homogeneous coordinates, it means that only that we rescale the homogeneous coordinate. Yes, by a factor. And to keep the structure of the linear problem, this factor should depend on the sum of all remaining variables. Yes? And in a standard way, we obtain a matrix linear problem now, but that factor, so psi of p plus 1 is proportional to psi 1. Yes? So the factor appears here, but it is not a constant. It is an arbitrary function of a sum of variables. And that system reduces to the finite, how to say, for a multi-component or p-component system. The old part is the same, and just the last equation contains that, how to say, non-isospectral factor. Yes? Of course, if it is a constant and central, or commutative with everything, that it cancels. Yes? Okay. And now we can find that that system, or in the periodic reduction, or in that full case, is three-dimensionally consistent. So, but this R, somehow it is not a scalar field. In the periodic case, it is a kind of P fields, yes. And in the full case, it is the somehow Z, so infinitely many components, yes. But geometrically, that consistency around the cube is a consequence of a Desargues theorem, which involves only somehow 10 points, not infinitely many fields. Okay, and as a side remark, we had also this type of system, yes, this equation. This equation, the system can be explicitly solved to what one can be called the non-commutative discrete KP map, and the fields Uij are now on edges. Yes. And somehow specialists know that from three-dimensional consistent systems on vertices, one can go to three-dimensionally consistent systems on edges. Okay, and now the final part, I would like to connect to something what is known for, I think, most of you. So let us consider situation that all variables commute. Yes, because so my motivation to study, for example, works of Kajiwara, Naomi, and Yamada was to understand geometry of Penlever equations. And in Penlever equations, something is important, that you need arbitrary functions. So before making reductions of integrable systems to Penlever equations, you need explicit dependence of functions of single variables. Yes. So we had one function of single variable, which is that mu, that non-isospectral factor. But now, what happens? That if you consider that P periodic equation, what you can find that if you multiply all solutions of that p-periodic case, you build a function R. Yes. So, and you try to somehow to find what is the equation for R. So what you do, you multiply all the equations, something cancels, and what remains? It remains such an equation. Yes, where here m is the logarithmic potential of that monodromy factor mu. And in the commutative case, this equation means that R hat is a product of functions of single variables. So this is the way, in my opinion, how one can consider appearance of arbitrary functions of single variables. Because, for example, let us consider the simplest reduction p equal 2. Yes, we have only two fields R1, R2, and arbitrary number of discrete variables. And somehow it is convenient to switch from gammas, the functions of single variables, to the square roots. Yes. So we know such a factorization. M is that logarithmic potential of the monodromy factor. Yes. And you can parameterize your R1 and R2 in terms of field X. Yes. And what you obtain, that X satisfies very well known non-autonomous lattice modified KdV equation with that additional non-isospectral factor. So mu1 is an arbitrary function of the sum of all other variables. Yes. And what happens in p equals 3, as one can expect? So here, instead of square roots, I use cubic roots just to connect with something known. And we can parameterize these three fields R1, R2, R3 with two fields. So we obtain a system for these fields. And one can find a closed form equation which involves 9 points of the two-dimensional lattice. And it is a version, I would say, non-isospectral version of the discrete Boussinesq equation I found in paper of Nijhoff, but it is related also to older works. Yes. And finally, somehow a posteriori, I would like to show you a way how to obtain all these commutative systems from the non-autonomous Hirota equation. Recall that we had some functions of single variables, and now I use explicitly that last variable. Yes. So let us redefine the functions in this way. That from the non-autonomous Hirota binary equation of Willox, Satsuma, and Tokihiro, we obtain this function. So we have, instead of three variables, I, J, L, I use the last variable written explicitly and somehow two arbitrary variables. So this is the form. One can define this function, in this case Rk, in such a way, and from that we obtain that three-dimensional consistent systems with infinitely many components, and the periodic reduction is given by such a quasi-periodic constraint on the level of tau function. Okay, so what I presented, I showed you how one can find some periodic reductions of the non-commutative Hirota system. Yes, and there are some some issues related with three-dimensional consistency of that multi-component system, and when making periodic reduction in the commutative case, we see that some arbitrary functions of single variables appear very naturally in the business, plus another function of, how to say, single variable because the sum of all variables is a single variable. That monodynamic factor mu was present in the equations. So that's all. Thank you very much.
Questions?
So you mentioned reductions to Pamave. I wondered, are there non-commutative Pamave?
I know that there are quantum Pamave. So at the moment I'm trying to do something for in the non-commutative case, following some known procedures in the commutative case. But I have not got any result.